Hi everyone. I am Sagar, and welcome to our um, this year last summer online public talk of Night Under the Stars. Um, yeah, so we hope you are doing well and you are taking necessary steps regarding COVID. And it's a really tough time, so we should focus our work to in productivity and some good stops. So we are also facing the same problem, and we are not or we are unable to conduct our normal live sessions. But thanks to the social media, we are now in social media platform and delivering our public talks. So today I am presenting about some something about the radio universe. It is a different part of the electromagnetic spectrum. So here I am starting my presentation. Yep. Uh, so this is our NUTS team, Night Under the Stars. We are foreign PhD students, and we are doing astronomy popularization work and astronomy outreach work in our observatory. So every month we are conducting our presentation and visiting around the observatory, those programs. But yeah, still, so this is our beautiful observatory. So now let's uh, start our talk with some basics. So my question is, what comes to your mind when you hear the word radio? So you can write what you are thinking about the radio and how it will be connected to radio astronomy. So yeah, I'm giving the 15 second, and I will check your comments. So yeah, I'm not seeing any comments now. Hmm. So I'm still waiting for some comments. I think the broadcast is slightly delayed in real time. So yeah. So yeah, exactly. It is a FM radio or a transistor device using which we can listen to different FM stations. We can listen. You have to just tune your knob or tune to some different frequency station. You will hear your favorite song or maybe some news or some any other important announcements. So, so this is so how the radio is related to the universe and how this device changed the not this device how the radio uh, universe looks like and how the what are the radio astronomers do using the radio waves. So that is the interesting part of our astrophysics. Yes. So at first at first we have to go for some basics. Yeah. Like how can we see an object? So when uh, when any object is there and it is reflecting the wave light and it passes to reach to your eyes, then you can only visible to a object. So there must be a light source and the source must not be sorry the object must not be a perfect observer. So light is an electromagnetic wave which consists of waves, and those waves you can describe using wavelength and frequency, a basic things of a wave. So yeah, so the wavelength is the distance between crest to crest or trough to trough of a wave. Yeah, so here you can see two waves. The red one is the long wave, and the below one is the short wave. So you can see the wavelength of the red one is the long, and the wavelength of the green wave is the uh, lower. So that means uh, and there is another term which is frequency, is the number of waves passed through a fixed position in given amount of time. So yeah, so this is the basics of any wave. And yeah, so here you can see that your eye can detect only a visible spectrum only. So your eye is an optical detector, and in this representation you can see as the frequency is increasing, the wavelength is decreasing, and it is vice versa also. Like when the frequency will decrease, the wavelength will increase. So that is the relationship between the frequency and wavelength. So the longer the wavelength, shorter the frequency, and shorter the energy also, and vice versa. And there are several type of wavelength. Like here you can see the radio to microwave, infrared, visible, ultraviolet, X-ray, and gamma rays. And yeah, so by consisting all those, we know this is the electromagnetic spectrum, uh, coming from gamma rays, then X rays, ultraviolet, infrared, microwave, radio waves, and extremely low frequency radio waves. So human eye only see this much of spectrum, which is also known as the visible spectrum, and we are going to emphasize this part of the wave, this part of the electromagnetic spectrum in this talk. So yeah, so so this is our atmospheric window, like how when light emitting from cosmic objects, different type of electromagnetic spectrum, how they are reaching to our earth or our ground. So which is called this atmospheric window to the electromagnetic spectrum. So here is the gamma ray, X-ray, and ultraviolet light, which is blocked in our upper atmosphere. That means the atmospheric opacity is 100% for those rays. And if you go to visible infrared spectrum, then the visible is coming to our ground, and after that the infrared, far infrared, mid infrared, and near infrared, and also the millimeter and some millimeter frequencies are also coming to the earth. But apart from visible spectrum, others are just blocked by the some part, or some part moreover blocked by the our atmosphere. But the radio wave, which can be observable from the earth, and those are longer wavelength, and they can easily penetrate the our atmosphere. And there are also some long wavelengths which is blocked by our atmosphere. So uh, so for different type of wavelength, or for different part of electromagnetic spectrum, we need different type of telescope to observe. um, According to the atmospheric window to the electromagnetic spectrum, we may put our telescope on the ground, or maybe in the sky, which is called observatories. So there are so each telescope requires a development in new technology, which is also n number of applications. um, like they creates really uh, big amount of data which is very hard to handle, and also the technologies required for each telescope is new for almost every telescope, so which also has human application, and yeah, to our humankind. So yeah, so astronomers also use a different type of wavelength to investigate the cosmos. So what is the advantage of studying the universe in different wavelength? So the conclusion is the different objects can tell different stories in different wavelength. So we are going to we are going to see those things in next slides. So yeah, so here is the galaxy which is known as the Centaurus A. The first you are looking at its optical image. So how it will be look like in infrared, then you have to use a different detector, and you will see it really looks different. And then ultraviolet detector or ultraviolet telescope, then you will see a different image of that galaxy. And then X-ray, which is the high energetic electromagnetic spectrum, you will see a different part of the galaxy with X-ray. And now coming to the radio, then you will see again a complete different image of the galaxy. So you can say that by combining all, you can know more about a cosmic object, and you have analyzed better rather than a single object. So now this is an example of composite picture of a typical galaxy taken from gamma survey. Here you can see like this one is the optical one. Sorry, this one is the this one is the optical one, the near infrared, mid infrared, and far infrared, and also here is ultraviolet image is also there. So by combining all those things, here it's produced a false image, and you can see the different structure of the universe, different structure of the of a object in different wavelength. Now yeah, so now this is the famous Andromeda galaxy M31 with a different part of the electromagnetic spectrum. Yep. So yeah, so now every wavelength sky reveal quite different parallel universe sharing the same space. So here the example of Whirlpool galaxy. So yeah, so here is the optical image of the Whirlpool galaxy. So you can see starlights and optical lights coming from the stars in that galaxy. When you switch to the infrared, then you can see also the light coming from the stars, but not regular stars, but older stars. And same when you switch to the ultraviolet, you can see the light coming from the large hot blue stars and young stars. So now coming to the X-ray, uh, you can see the high energetic photons coming from the galaxy, probably from any X-ray source or center of the galaxy, or any so this part the center of the galaxy, or some dots are X-ray source which is from X-ray binaries. And now at last the radio. So the radio waves reveals a different part of the galaxy, because the cool gas and like some molecular CO2, molecular hydrogen, those are emitting radio emission from this for this galaxy, and those are visible in the radio spectrum. So yeah, so we will focus some part of the radio, and we will see how it some history of the radio, history of the radio astronomy, and how it started, and just some brief idea of radio. Yeah, so here is the some basic part of the radio wavelength. So now the radio wavelength consists of uh, four types. Sorry, now it is subdivided into four types. like microwave, millimeter waves, sub-millimeter waves, and radio waves. So microwaves ranging from 1 centimeter to 30 centimeter, and millimeter is 1 millimeter to 10 millimeter, and some millimeter is less than 1 millimeter but up to 0.04 millimeter. Uh, and rest part is the radio waves. So the longer the wavelength, we require a large size of telescope to get the radio wave into the telescope or into the detector. You can the good thing about the radio observation is you can observe the radio sky in daytime also, because uh, there is because radio waves not blocked by any atmosphere, or there is no like an optical image. You have to wait to night because sun is too bright to observe the optical or visible sky, but in radio you can easily observe the radio sky in night times. So radio telescopes are look like parabolic dishes, like your dish TV antenna, not like a traditional optical telescopes. So yeah, so here is the optical telescope that usually used by amateur astronomers, but the principle is always same for all telescope, like big telescopes also. But as we require the longer wavelength to catch, so that's why the radio telescopes are bigger, and they used as a parabolic disc. Those are metabolic parabolic dishes which can catch the radio wave, and those are amplified by the amplifier and then stored into the computer. And the the radio waves are so less energetic, that's why we need to amplify the signal further for the detection of the spectrum or the radio observation. So yeah, so now coming to the some history of our radio telescope. Uh, so many of may know that the Jagdish Chandra Bose, uh, he's from India. He was from India. He was the inventor of radio and many more things. J.C. Bose in particular investigated the properties of the wave and material into the short centimeter to millimeter wave part of the spectrum. He used some simple setup devices, and he really performed some experiments in millimeter waves. Later, the Marconi makes it commercialize the radio. He solely investigated the millimeter waves when nobody known about this field. So that's why IEEE named him as the father of radio science. Yeah. So so first, when the radio sky is observed, or how it discovered, now we have to go to the 1930s, which is in between World War II and World War One. So in Bell Laboratories, a young radio engineer named Carl Jansky was studying an unknown radio interference coming from the sky uh, by his some instrument, which is for this study he built a telescope or built a device which is look like this, and which records the 20.5 megahertz frequency at 14.5 meters, and they like it is rotating around on a sliding on a round type of base, and that's why it's famously known as the Jansky's merry-go-round. With this uh, instrument, he figured out the some radio interference or radio emission is coming from our center of our galaxy, which is Sagittarius A, and then he surprisingly discovered the center of our Milky Way, which is emitting uh, radio waves, and for this he is now known as the father of radio astronomy, and after his name the uh, BLA, very large area telescope, Carl Jansky very large area telescope is named after him, and also the unit of the radio uh, unit of the radio uh, flux is also measured using Jansky unit, which is named after him only. So yeah, so after his work, Carl Jansky left the work, and he was happy with his engineering work, so he left this field. But by inspired from the Jansky's work, and another radio engineer, Grote Reber, applied for jobs applied for jobs several times to Carl Jansky to the at Bell Laboratory, but due to the World War he couldn't there was no fund and he couldn't find the job, so he decided he had to study the radio astronomy by his own. So in 1937 he came up with an idea, and he designed a radio telescope in his backyard, with in his free time and with at his own expenses. So this was the first radio telescope in the history of radio astronomy, and he first time mapped the radio sky. So this is the sky he mapped, some Milky Way and the its center, the Sagittarius A, and so that's why he known as the first radio astronomer in the radio astronomy field. So yeah, so now come to the this image. So now let's start the how different part of the universe look in radio wavelength. So this is the optical image of the sun, and this is the sun which is look at the radio wavelength. And yeah, so this is the Jupiter which is visible in the optical wavelength, and if you see the radio image of the Jupiter, then you will see a complete new thing about the Jupiter, that something is coming out of its like a bipolar direction, which is the synchrotron emission. And yeah, so here you can see the optical image of a galaxy which is famously known as the Hercules A, and if you see it is in the radio wavelength, it is look like a different entire different object. Yeah, so this is the radio emission coming out from that galaxy. You will see that the radio emission is quite bigger, quite maybe 10 times larger than the optical emission. So that's why the radio astronomy is giving the some fascinating things of the astronomy, and you can really know more about the cosmos using the radio wavelength. So now coming to this image that I have used for my poster. So here what you can see, those three are radio telescopes, the three antennas of Giant Meter Wave Radio Telescope GMRT, and what you have see, it is not a normal sky, it's a radio sky. Here it is I photoshopped just in background, but those sources are not present in that same sky, but I put from different part of the sky, and I combined 5 and 4 images. So how those things are look like in optical or in and in radio wavelength. So here is the first galaxy 3C449, how it is look like in optical. So you can see it is look like in optical. This is a Pan-STARRS image, which is a optical telescope which imaged that part of the sky in optical wavelength or the visible wavelength, where what our eye can detect. But if you see the same thing in the radio wavelength, you will see a different thing. So a jet-like thing coming out from the center of the galaxy, and which is quite longer, and which is quite bigger than the optical image. And now coming to the next galaxy, which is 3C236, which is a famous radio galaxy. If you see the same thing in the optical image, you barely visible, you can barely see its host galaxy. But if you put this part of the sky in the radio wavelength, then you will see a complete different picture, and the radio emission is coming from the galaxy, which is again a jet direction. Due to the beaming effect, the one-shot jet is not visible. And now coming to the next galaxy, which is 326, which is a famous galaxy. And again, if you see it in the optical image, you will see the you can barely see the uh, um, just the small dot, the host. And but if you see the radio image, you will see the whole lot different thing, that the bipolar jet type of thing is coming from the center of the optical galaxy, which is completely um, invisible to our eye. So now coming to this one, which is IC711, which is a head tail galaxy. If you see in optical, you will just see just a dot, which is the host galaxy. But if you same thing you will see in the radio, then you will see this one, which is a really a big radio structure coming out from this galaxy. So now coming to the last one, which is 3C129. If you see this galaxy in optical, here you can see the optical part of the galaxy, which is a very tiny one. But if you see the same thing in the radio, you will see a really giant radio feature, which is coming out from the center. So yeah, so this is the story behind the poster, and this is the small journey to the radio sky. And yeah, from here I am so yeah, so I am dedicated this talk my talk I'm stopping my talk, and I dedicated this talk to the late Professor Gobind Swarup, who passed away recently on 7th of September. He was one of the pioneer in radio astronomy field around the world, and he is known for his best research facility created in India, which is Giant Meteor Radio Telescope and the OT Radio Telescope. So GMRT is Giant Meteor Radio Telescope, which is still the largest parabolic steerable dish present in the world. And yeah, so he has really done some nice work, and he also formed the Indian Radio Astronomy Group. Yeah, so I'm dedicated this talk to him, and yeah, from this I am ending my talk, and those are references. And thank you, and I'm waiting for questions. And thank you for joining us. And yeah, you can ask questions, and I will see through comments, and I will tell whatever. Yeah, thank you. So here is the first question from Sir Suresh Kumar. Um, the radio wave is a range of sound waves. Sir, the sound wave is a different um, thing which is corresponding to sound, but radio wave is corresponding to the light. Like the light you are seeing, it's a visible range, but the uh, uh, what the radio waves are similar to the uh, electromagnetic spectrum, but the wavelengths are completely different. What I have shown um, in first place, like yeah, you can see here, like there are radio waves which is larger waves, and what we see is the visible uh, part of the spectrum. Yeah, so I'm not seeing any questions. I don't know why, but yeah. So here is the question from uh, Christiana. How do they transform the radio signal into the visible picture in colors? For example, we could see a radio wavelength picture in blue and white. How do the device, which radio wavelength should be colored blue and which is white? So the radio images you have seen, those are really the false images. So let me come to this part of that. So here you can see the optical image, which is directly visible to your eyes, but the blue color what is visible is the radio emission coming from the Hercules A. Um, but how it is blue? It's because uh, you know that the astronomers are really intelligent, that what they are doing, they just merge the different wavelength frequencies in different channels. Like if you take three channels like red, green, blue, if you put red color in red color, if you put the radio wavelength, in blue color if you put the optical wavelength, or in uh, green color if you put any other frequency, then you will just see the different uh, wavelength in different color. Like here you can see the radio images looks like a blue. It's because it's in a blue filter, and here the optical image look like a whitish. It's because it's uh, it's a combination of three filter actually. But here you can see the infrared is in red filter, and the ultraviolet is also in blue filter. So those are just false images. So how you can measure the radio signal is like we just uh, uh, take the signal from the sky from using the radio telescope. Yeah, using the radio telescope, and all waves are reflected here at the center, which is called the horn or the radio receiver. Then it is transmitted to the amplifier to amplification. Then again it converted to the, like how much intensity you get from which point of the sky. Then they are imaged like this. It just depending on the intensity, and also they do Fourier transform of the signal to uh, because I don't know how to explain it. Uh, you just say that it's just a Fourier transform of the signal, and now it's the false image what is visible to the radio sky, radio image. So yeah, so the next question coming from the Archana, what information we usually gather when we compare optical and radio images, and why they are different? Uh, yeah, it's like you can say that you are looking at a human body with your eyes and with your X-ray and with X-ray telescope, with X-ray, like with your eye you can see just the body or the just the outer visibility of human body, but if you use the x-ray then you will see the bones. It's because x-ray can penetrate the bone, sorry, x-ray can penetrate the human body and reflected from the bone, then you can see that x-ray image of a person or of a human being. So similarly, if you observing a cosmic object, if you want to see in optical or in optical telescope, whichever part is emitting the optical photons or the visible photons, that can be visible in the optical telescope, and whichever part is the emitting the radio photon, that is visible in the radio telescope. The difference is the processes, because different wavelength is corresponding to the different temperature according to the blackbody radiation. If you go to the thermal radiation, then there are thermal radio emission is there. Apart from that, when you observe a galaxy, like come to this one, the Cygnus, sorry, the Hercules A, whatever the blue part is visible, which is in radio spectrum, which is the synchrotron emission coming from the center of that supermassive black hole, which is emitting the jet, and using the magnetic field, particles are spiraling around the magnetic field and due to the Lorentz force, and now they uniformly distributed like a bipolar jet. It's due to their relativistic motion also. Yeah, so any other questions? So here is a question from Pratyasha Singh. How is radio astronomy and remote sensing and hyperspectral simulation is related? Because in radio science we use, or is radio science we use the same concept to study the geomorphology of rocks. I'm not exactly know about the remote sensing science, but yeah, I can say that I think for communication purpose we can use the radio signals. It's because radio waves can transfer anywhere, like there is no barrier to radio signal until and unless there is a magnetic plasma is not present. So I think for communication purpose we are using the radio signals, like while if you see that the Chandrayaan mission, engineers and scientists give command from the ISRO, and they are, and the orbiter or the probe getting the signal from the earth, it is via the radio signal. And yeah, I know that much, but I don't know much about how they are using in remote sensing science. So Soumya Ranjan is asking a question: what is the future of radio astronomy with so much of interfering devices? Would it be possible from Earth? So we should move our telescope to the moon. So yeah, so an important discovery of the radio astronomy was the last year we have done, which is the Event Horizon Telescope, which helps us to detect the central supermassive black hole, the presence of central supermassive black hole in M87. The accretion disk is completely visible in this image, and it is due to due to the radio astronomy science. They use the same thing as the interferometer, where they combined the uh, number of telescopes around the world, and they made a telescope which is similar size of Earth, and then they only catch the signal of the central part of the, or they uh, able to see, or that resolution is enough that you can see the center of M87. And yeah, so interfering devices are also create problem for radio astronomy. So before making a radio telescope, um astronomers and even if engineers, they together um, see the which part of the uh, radio spectrum is reserved from which application of the humankind. Then they just omit that part, and they're making observation just the rest of the spectrum. And I think there are some part of the spectrum which is reserved for radio astronomy. But if some interfering devices will come, then it will be create problem that it will interfere always. And yeah, for interfering devices like mobiles, electronic instruments are also creating interference during the radio observation, including even if our ground, human body, and also the instruments in the radio telescope, those are also creating the interference, which is also creates the problem while observation. But during the design, they take care of all those things. They just cut out the every noise and uh, those things, um, and then only the radio observation make possible. Yeah, we can move our telescope to the moon, but I think it will take some time, and it will be good if we make a long interferometer using moon and Earth. But yeah, I think in future we will do. So any other questions before inviting? So one question coming from Syed Umair. What is the size of the universe in visible and radio wavelength? Is there any much difference? So if you see this, like in my point of view, I may be wrong. In my point of view, the size of the universe in different wavelength is like um suppose you have a uh, 10 meter or 10-meter ball or a 10-meter object. It's the central 5 meter is only emitting radio, and the entire 10 meter is emitting the optical. Then it's hard to distinguish that the size of what is the real size of the ball in radio wavelength. But I think for universe, uh, uh, the large extent we can see through the radio telescope is, I think it's cosmic microwave background, because microwave also coming in the radio region. And yeah, it really looks different than the our real sky. And the size of the universe, yeah, to get the size of the universe, we have to know that whether the extreme parts of the universe are emitting in radio or not, or because radio emissions is coming from the synchrotron, um, inverse Compton, and thermal radio. And yeah, so I will say that much only. I'm not that much of aware of all those, like how it will look like. Any other questions? So I think there is no other questions. Yeah, so yeah, I think there is no other question. Um, stop my live video here. Thank you so much for joining, and I hope we will do such kind of events or more good events like this in future. Thank you all for joining. Bye bye. Good night.